Exercise 1. Develop a math model for the following problem. If the model is a linear programming problem, solve it manually and interpret the solution. An office supply merchant wants to send a team out to sell file cabinets at an outdoor market on Saturday. The merchant wants to sell two types of file cabinets: a 2-drawer vertical file cabinet, which the merchant can purchase wholesale at $100 and sell at $155, and a 2-drawer lateral file cabinet, which can be purchased wholesale at $200 and sold at $350. The merchant has $22,500 available to make the wholesale purchases. The company truck has a storage volume of 1,140 cubic feet. Assume, if necessary, that the cabinets can be packed to entirely fill this volume. Each vertical file cabinet has a volume of 4 cubic feet, while each lateral file cabinet has a volume of 12 cubic feet. The merchant is confident that all cabinets brought to the market will sell. For maximum profit, how many vertical file cabinets and how many lateral file cabinets should be brought to the market? Alright, what comes to mind perhaps immediately is, for choice of some variables here, we probably will let x equal the number of vertical file cabinets to bring. And then y will, of course, be the number of lateral file cabinets to bring. The key quantity in this question is this profit. Of course, the merchant wants to make the most profit. So let's let P equal profit. And profit is, of course, revenue, money coming in, minus costs. And what's that in this case here? We can even make a formulation, because right here we have, for instance, the one vertical file cabinet purchased wholesale at 100 sells at 155. Okay, so 155 minus 100, $55 profit on one. If the merchant sells X of them, that would look like 55X for the profit on all the vertical file cabinets. Similarly, there could be some profit on the lateral file cabinets, one of which wholesales at 200, sells at 350. Okay, 350 minus 200, there's our profit, 150 on one, so 150 times y for the entire lateral cabinet profit. So, okay. Now there's our profit function, and since this is kind of important, maybe label this as the objective function. And of course we are trying to maximize this. What about some restrictions on x and y? What about this domain? Subject to, well, first we can talk about just physical sense. We're talking about x and y each being the number of file cabinets to bring. Okay, well, that alone would have us say x has got to be greater than or equal to 0, and y has got to be greater than or equal to 0. Another thing, because they are numbers of file cabinets, x and y are integers. Also part of the physical sense there. Okay. Let's see, what else have we got here for restrictions on what x and y can be. The information, we read along here. Okay, the merchant has $22,500 available to make wholesale purchases. Okay, so let's write down wholesale purchase budget. Okay, what about that? Alright, well, each vertical file cabinet has a wholesale price of $100, so 100x is the wholesale money spent on all the vertical file cabinets, and similarly, the lateral file cabinets wholesale at $200 each. That would mean we're looking at 200 times Y for all the wholesale money spent on lateral file cabinets. And this amount here has to be less than or equal to the $22,500 in the budget. Okay, maybe we call this, well, let's call this physical sense inequalities 1. Here's inequality 2, part of our domain requirement, and perhaps you might want to simplify this a little bit right away. For instance, both sides you can see divide evenly by 100 right away, so perhaps we could say x plus 2y less than or equal to 225. Okay, we call this 2a, since it's derived from fundamental inequality 2. Let's see, anything else we have here? Yeah, the company truck has a storage volume of 1,140 cubic feet. Okay, and we have got to pack our file cabinets into this volume here. So we basically have here a volume limitation. Now, we're told that each vertical file cabinet has a volume of 4 cubic feet. If you have x of them, your volume ends up being 4 times x, plus the lateral file cabinet has a volume of 12 cubic feet. If you have y of them, you're going to have 12y of a volume there, and that's got to be less than or equal to 1140. We could call this inequality 3 here. While we're staring at this, it looks like, okay, yeah, both sides will divide by 4 evenly. Maybe we go ahead and do that now. X plus 3y less than or equal to 4 goes into that, let's see, the 11 there goes 2 times 8, carry the 3 down, 34, 8 for 32, 205. Okay, 285 divides that, and we could call this 3a. Okay, we seem to have accounted for everything that's in the statement of the problem with our math model here. Let's take a look at this math model. Alright, we're maximizing this profit P here, which is a linear function. Okay, linear function being optimized. So far it's like a linear programming problem. Now, what about the domain? What about the constraints? We need to see all linear constraints first of all, and we have that here. Wait, do you see this? X, Y are integers. Okay, you know what? That actually disqualifies this from being a linear programming problem. This is actually an integer programming problem because of this constraint here. Okay, so it seems a little bit bleak at first. There's some good news possible, though. We have to wait and see. The rest of these, you notice, are linear inequalities. Okay, so here's our one problem, this integer thing. Turns out, if we sketch up the domain, or feasible region, and every vertex has integer coordinates, then we can solve this just like a linear programming problem. Okay, so let's make a note of what we've just observed here. This is not a linear programming problem, but rather an integer programming problem. However, due to all of the rest of things being like a linear programming problem, we have a big if here. If each vertex of the domain has integer coordinates, we can solve this as a linear programming problem. Okay, so let's see if we can still succeed with our linear programming idea to solve this question. We need to get the graph of the domain or feasible region in order to proceed further. Alright, so we're getting ready to sketch up the graph of this domain. Let's look over what we have here. Alright, x greater than or equal to 0, y greater than or equal to 0. Alright, so we just need to get the first quadrant in our coordinate system. We're kind of just ignoring this integer thing here for the time being. This inequality, let's see, the boundary line, I'd like to get the intercepts. I'm going to need an x at 225, a y at 112.5. This one, when I graph the boundary line, I'll need an x at 285, okay, nearly 300, and a y at about a third of that. Okay, get an idea for what kind of coordinate system might fit matters here. I think to get, say, 300 along the x-axis, I'll go with 25 units per centimeter. Okay, so this x-axis here. And the y-axis not nearly so long. Okay, so here's x, and since it's a real problem, I actually like to try to put down in words what this is here. So this is the number of the vertical file cabinets, and symbolically this is y, and in words this is the number of lateral file cabinets. Alright, so it's 25 per tick mark. 1, 2, 3, 4. 100. 1, 2, 3, 4. 200. 1, 2, 3, 4. 300. 1, 2, 3, 4. 100. Okay, let's see if this works out for us. Alright, getting a contrasting color out. And going to the inequality 2a here. Alright, when y is 0, x is 225. Okay, that's actually right on a tick mark. To emphasize that is indeed on a tick mark, I like to put the number right there. In the other case, if x is 0, y becomes 225 over 2, 112.5. Okay, here's 100, there's 125. It's exactly between 112.5 and there. We're hoping this does not end up in our domain, because at 112.5, not an integer, that will fully disqualify this problem from linear programming treatment, forcing it into the realm of integer programming. Okay, there's the boundary line. Let's label its equation. That was 2a there, x plus 2y equaling 225. As the inequality shading goes, let's see what to do here. I will test 0, 0 into this inequality. 0, 0 less than or equal to 225 is true. It's 0, 0 side of the boundary line that gets the shading. I just use a light shade to just keep track of matters here, because I need to eventually get the intersection of all of these half planes. And time to move to the second inequality. Another contrasting color, red for now, right here. Alright, if y is 0, x is 285. Okay, I'm going to give that coordinate a nice label. Here's 275. 285 would be 2/5 of the way along that little section there. Okay, 285. And solid dot. What happens if x is 0? Now we have 3y is 285. Divide both sides by 3. 3 goes into here. Let's see, 9 for 27. 15 left over. 5. 95. Okay. Now let's make 95 clear. Here's 75. Here's 100. 95 is right there. And solid dot. And now the boundary line, which by the way is solid, right? Because this is an or equals to inequality we are graphing. Okay, let's label this boundary line with its equation. This would be 3a here, x plus 3y equals 285. And as we test our 0, 0 point here to see which side of this red line to be shading for its solutions, 0, 0 less than or equal to 285 is true. It's the 0, 0 side of this line. Now we intersect that with the previous, and we realize that we are in here for our domain. Okay. So here. Okay, now we could come in here and label this as feasible region. And what's really important are going to be the vertices. So let's see there. And we have here, that's the 95 for the y-coordinate. Great, it's an integer. It looks like we're on our way to succeeding with a linear programming type solution, despite this being an integer programming problem. And here's 225. Okay. And of course, 0, 0. Thankfully, this 112.5 point for y-coordinate, this is not in our feasible region, and that's good because that allows us to proceed along here as if this was a linear programming problem. Oh, wait a minute. What are we? Too soon to say for sure. What about this? What are the coordinates? Okay, let's figure this out. Let's go up here and work on this problem. That's the asterisk. Come here and look for our work. It's the intersection of the red line and blue line. Okay, the red line, x plus 3y equals 285. The blue line, x plus 2y equals 225. Looks like this system is ready for some elimination. How about first equation minus the second? X minus x, x's are eliminated. 3y minus 2y is y. 285 minus 225, 60. Okay, let's look for some graphic consistency before we go further. Does this point look like it has a y equal to 60 These are 25 apiece, 50, 75. Yeah, looks consistent with the graph. Keep going. We can use the second equation as a source of getting x now. That will be the 225 minusing 2y, or 2 by 60. And what's that give us? That's minus 120. That gives us 105. So this becomes the point 105.60. Does that 105 look consistent with the graph? Here's 100. There's 125. Yeah, this looks pretty good. Okay, now look at these vertices. Each has all integer coordinates. We are ready to proceed with our linear programming analysis of this situation. Off to the table where we evaluate the value of the profit function at each vertex. Okay, so for our table here, vertex, and evaluate the profit at each of these. The formulation we had for profit was 55x plus 150y. Okay, for vertices we've got 0, 0, we've got 0.95, we have 105.60, and we have 225.0. Okay, well, this one, of course, is 0. That's probably our minimum profit. Take nothing. Okay, this vertex here, let's see, 0.95, that amounts to 0 plus 95 by 150. Okay, some scratch work on the side here. I'll do 95 by 15 and add a 0 when I'm done. Okay, so we got 25, 2, 45, 47, 0, 5, 9, 5, 12, 14, and add a 0 to make up for that. And that would sum to 14250. Okay, let's go to this next one here. This will become 55 times 105 plus 150 times 60. Okay, 55 by 105. Alright, I can just do 55 by 100 at first. That would be there. And then 5 by 55. Let's see, that would be 250, 275. Okay, 5775. Okay, so this goes on to become 5775 plus, alright, 150 by 60. Okay, I can do 6 by 15 and then add 2 zeros to it. 6 by 15 is 90. Okay, add 2 zeros, brings us to there. And now we add these two together. We're up to 14,775. Okay. Last vertex, 225 by 55. Okay. I guess there's... Here we go. 25, 2, 12, 11, 0, 5, 2, 1, 1, 5, 7, 3, 2, 1. Okay, so this equals 12,375. Okay, we're trying for maximum profit. It looks like right here. Okay, it came from the vertex 105.60. Guess we can make our conclusion interpreting what's going on here. Looks like we believe a maximum profit of dollar symbol now 14,775 can be achieved by bringing 105 vertical file cabinets and 60 lateral file cabinets. Okay, big cloud around this conclusive statement. And as some sort of check here, let's see. Now, in an application problem, it's not really the math that you question, because it's that translation from real world into math model where most of your mistakes lie. So we want to have this kind of make physical sense to us. First of all, we like these integers for numbers of cabinets. That looks good. Let's do a kind of a quick check over on the volumes here, for instance. Here, let's see if these volumes really will fit into the truck here. Just kind of redoing it. The volume. So we have 105 vertical cabinets. That's 105 times each vertical file cabinet had a volume of 4 cubic feet. And then plus, we got 60 of these lateral cabinets. Each has a volume of 12 cubic feet. Let's see, this would give us 420 plus, let's see, alright, 6 by 12 is 72, add a 0, 720. We're up to 1140 cubic feet. Okay, that will fit in the truck. Exactly fits in the truck. Okay, so that's in order. And let's also check the wholesale price. Okay, let's see what we do here. That gives us 105 of those vertical file cabinets. They wholesale at 100 each. And we have to add to that the fact that we got 60 lateral file cabinets, and they wholesale at 200 each. Alright, let's see what we get here. This gives us 10500 plus, this would be 12 with 3 zeros following it. We're up to, let's see, 22,500. And that is indeed the exactly the budget for wholesale. We maxed out that budget. Okay, so you know what? The solution looks pretty good now. I think we pretty much got it. And notice the good fortune here we had in getting those all integer coordinates to these vertices. This enabled us to solve this integer programming problem as a linear programming problem. Pretty nice. Okay.